All right. Okay. So we're going to start a topic. So we're going to. What just happened? Oh boy. Okay. Hang on. Let me. Something just. Give me a second. Okay. All right. So we're going to start the topic. So again, letter C. Okay. We'll look at Markov chains. Okay. And today we're just going to introduce the topic. We won't even do any Markov chain Monte Carlo. Just introduce the concept of Markov chains. All right. So the reason why we're going to do this, okay, is basically big picture. This whole class, what we want to do is we want to learn properties about some probability distribution. Okay, so this is what we want to do. And again, the reason why we turn to Monte Carlo methods is that, the distribution is too complex for direct analysis. Okay, and so what we've already covered is that we will, so instead of direct analysis, we will approximate the distribution by drawing a random sample from the distribution. So by drawing a random sample, okay? And we've already covered many methods. The whole first 3 weeks was talking about how we can draw random samples from different shaped distributions, okay? So, this was heavily covered for multivariate, or for univariate distributions, right? Heavily covered in weeks 1 through 3 for univariate distributions. Okay. But for high dimensional distributions, the methods that we've covered can become very inefficient, okay? Our methods can be very inefficient, okay? And so, theoretically, as n goes to infinity, it will converge to the actual distribution, right? So, but we don't have infinite time, okay? So theoretically, our methods converge to the target distribution as n approaches infinity, okay? But, we don't have that kind of luxury. We don't have that much time. So we're always dealing with just a finite random sample. Okay, and this is often a problem when you have a very sparse distribution, okay, which is often the case. Okay, so we often have, and I think I've already talked about this already, but we often have very sparse distributions okay? Which means, most regions are very close to 0, and only a small region has values of interest. Okay, so here's a univariate example. Generally, we're dealing in high dimensions. Okay, but here's a univariate example where we could have the normal distribution, and if we go from, let's say we go from z equal to minus 25 to z equal to plus 25, the normal distribution will look kind of like this, where pretty much anywhere from -3 to -3 to -25, the probability density is, practically 0. It's not exactly 0, but it's practically 0. And then, from +3 to +25, it's again also practically 0. And there's really only a small pocket here, okay? And can you imagine what if we did rejection sampling using a uniform proposal distribution, uniform -25 to +25, okay? Like 90-something% of those values that it proposes are going to be rejected, and we're only going to be accepting, only values that are in this tiny little hill will be accepted, and pretty much everything else will be rejected, okay? So if we did rejection sampling, okay, we would have a very low acceptance rate. Okay, and that would be very inefficient, right? And so Markov chain Monte Carlo will give us a more efficient sampling scheme, okay? Efficient way to sample. Okay, however, today we won't even get to talk about the algorithm that we would use to generate samples, okay? That's like next lecture, the lecture after, okay? First, we got to just talk a little bit about like Markov theory and I don't know, this boring stuff. Not boring, but just we have to cover some groundwork before we can get into drawing a sample, okay? All right, so we first have to cover some groundwork. Markov chains. Okay, so I'm going to draw a two-state Markov chain. So we have two states, A and B, and the idea is if you are at A, there is you might transition to B. And if you're at B, you might transition back to A. So we'll just start off with, say, two possible states, A and B. Okay, and if you are at A, you might transition to B, okay? Or if you're at A, you can also end up back at A, okay? If you are at A, you might also just stay put, okay? may also stay put. Okay, same as B. Okay, if you're at B, you might transition back to A. You might stay put at B. Okay, so we have probabilities to transition from one state to the other. And then there's also probabilities. We have probabilities to remain in the same state. Okay, so for an example, we can say weather might, we could say there's two states. In California, it's either sunny or it is not sunny. Okay, that's what we will say. Is today sunny? Kind of, I don't know. Whatever. We might some debate here. All right. Okay. And basically, in California, it's either going to be sunny or not sunny, and so not sunny would include like rain and clouds. And is there any other weather you get in Southern California? Rain, clouds. Huh? I mean, I guess in the very rare chance that it snows or something, that would be factored in there, okay? And it might, the weather might go something like this, right? The weather in April or May, it might be like sunny, 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 and then it becomes not sunny for a couple days, then it becomes sunny, then it becomes not sunny, and then it goes back to being sunny, or something, And then once you hit June, it's just A for, 90 days. All right. Okay. So this is what we have, and so there's I don't know, something like this. Okay. We have something called the Markov property, and this is the kind of the defining characteristic of a Markov chain is that it is memoryless, all right? Which means the next state, the probability of the next state depends only on the current state. Okay, so where you end up next only depends on the current state. Whatever happened in the past doesn't matter. It's just where you are now. Okay. So if you're thinking of a board game, okay, and like Monopoly, and you're just like rolling dice to see where you're going to end up next. Okay. The probability of where you will end up next depends only on your current position on the board. Okay. Where you were in the previous turns has no bearing on where you're going to end up next. Okay, so that would be an example of a memoryless kind of having this Markov property, right? Whereas, other things in life, maybe it depends on not just the current state, but maybe the previous states. Okay. But we, and who knows, weather might not actually be have this Markov property, but we can say, let's just approximate it, and because we're just making simplified models, right? Because when we make a mathematical model to model a real life thing, we're not saying we want to recreate this real life thing exactly. We just want like a simplified version of it. Okay, so we're not going to try to understand all of the weather and what's meteorology and whatever, but we're just going to say, based on today's weather, we can try to predict what's going to happen tomorrow, okay? And we're going to say tomorrow's weather only depends on the weather today, not the weather from a week ago or something. Okay, and so when we have something like that, we've got to build something called a transition matrix. Okay, and the transition matrix will represent kind of your current states and the next state. Okay, so if you are at A, the next place you can end up is A, and so here's A and here's B, and so if you're at A, you can end up back at A, and we'll say this is maybe happens with probability 0.7, which means we will end up at B with probability 0.3. Okay, so I will write 0.7 and 0.3. Okay, and then if we're at B, we can go over to A, or we could end up back at B. Okay. I don't know, what should I say? The probability of going from B to A, we will say is 0.4 and 0.6. Okay, is that all right? Okay, and all right, so that means, if today is A, then the probability, so this is what the matrix are, probability that tomorrow is A is 0.7, okay? So we have a transition matrix. So this just represents transition probabilities. Okay, and we'll often call our transition matrix the matrix P. Okay, so we'll have transition matrix P. Okay, there's some properties about Markov chains, okay, that are important, okay? And so there's something called ergodic or irreducible. We'll say a Markov chain is ergodic or irreducible if you can reach all other states from any state. Okay, so if from any state you can reach all other states, then it is ergodic. Okay, so if we have this, okay, this is ergodic because from A you can reach B, and from B you can reach A. All right, A can get to B, and B can get to A. This exists, and this path exists also. Okay, and if you have A and B, and I'm going to draw these circles bigger. Okay, you don't need to have a direct path. Okay, you could have this, and this is also ergodic, okay? Because a path from A to all other nodes exist, okay? And then, from B, you can also reach any other node. Like if you're at B, you can reach A. You have to go through C and D first, but you can also get to A, right? So B to A also, and all other nodes also exist. Okay, so this is fine. Okay. However, if we have have something like this. Okay, this is not because you can go from A to D. You can get from A to B or A to C or A to D. Those paths exist. But once you are at C or D, there's no path that gets you back to A or B. Okay? So no path from C to A exists. Okay? So this is a problem. Okay? All right, is that okay? All right, and then there's another thing called a chain can be periodic or aperiodic. Okay. So here, this would be a periodic chain, okay? A chain is periodic if certain states are only possible at certain times. Okay, so if we start at A, then it goes A, B, A, B, A, B. You know, A happens only on the odd states, and B happens only on the even states. Okay, something like that. So this would be a periodic, right? Okay, aperiodic means basically a state can show up kind of anywhere in the sequence. It's not limited to just certain periods. Okay, all states can show up kind of, you know, anywhere in the sequence. Okay, they're not limited to certain periods. Okay, and so to make something aperiodic, whoops. So we're going to have this. As soon as a state, as long as there's one state that can return to itself, okay, then it will be an aperiodic chain. Okay, if a state can go back to itself, can like remain unchanged in the next kind of phase, then the chain will be aperiodic. Okay, so you can go A, B, A, B, A, B. You can also go A, B, A, B, A, all right? And so on and so forth, okay? Et cetera, et cetera, et cetera. And so you can see how B can show up on the evens or the odds, you know, as long as something happens where, so, you know, basically A or B can show up on even or odd, kind of odd times. Happens only on the even, odd, I should say, not states, but intervals. Okay. All right, is that okay? So we've got kind of these two definitions, something that's ergodic or irreducible, and something that is aperiodic. And again, kind of the simple thing is if you see a state that can remain unchanged, like it transitions to itself, okay, as long as at least one of those transitions are possible, then you're going to have an aperiodic thing, okay? All right, and so anyway, we can use the transition matrix to figure out kind of the distribution of things after applying the transition. Okay, so we'll go back and we've got this thing, and we said going from A back to itself is 0.7, A to B is 0.3, going from B to A is 0.4, and B back to B is 0.6, and our transition matrix P looks like this. We've got A, B, A, B. A to A is 0.7, A to B is 0.3, B to A is 0.4, and B to B is 0.6. Okay. Okay, so we use the transition matrix to find the distribution at the next step. All right, so let's say we start where 100% are at A and 0% are at B. Okay, so I would represent this with 1 and 0. Okay, so this is this matrix, this row matrix represents my distribution. Okay, so I got 100% at A and 0% at B. Okay. If if we have like 100 people and then we say, all right, you're going to undergo this transition where 30% are going to go to B and 70% are at A, what will be my distribution? At the next iteration, what will I have? A will be, so we got 100% at A, and we're going to say 70% will stay at A and 30% will go to B, okay? What do we have? We're going to have 0.7 here and 0.3 here, okay? And I want to show that this is actually all we have to do is we just multiply it by our transition matrix P. So I've got 0.7, 0.4, 0.3, 0.6. And we can see that if I do 1 times 0.7 plus 0 times 0.4, I would get 0.7. 1 times 0.3 and 0 times 0.6, I would get 0.3. All right. Okay. All right, and so after one iteration, I've got 70% at A and 30% at B. Okay. What will be the distribution after one more step? Okay. I have 0.7, 0.3, 0.4, 0.6, and basically what's going to happen is that, okay, I've got 70% at A. Of that 70%, 70% will remain at A. So I have 49% remains at A. I also have 30% at B, and of that 30%, 40% of those, so a total of 12%, will move back from B. We'll move from B back to A. Okay, and so here after the next step, I would have 0.61. And then over here, I have who's going to end up at B? Okay, well, I've got 70% at A, and of that 70%, 30% for a total of 0.21 will go from A to B. So this is A to A and B to A, and this is A to B, and this will be B to B, okay? And then I've got 30% at B, and of that 30%, 60% for a total of 18% will remain at B, so I have a total of 0.39. So after the second phase, I have 0.61 and 0.39 distributed between A and B. Is that okay? And so I can kind of see by multiplying my current distribution by the transition matrix, I can see where things will end up. I don't know if I... So this is going from A to A, and this is B to A. A to B and B to B. Okay. Is that all right? Does that make sense? And what can happen is that, what we want to find is we want to find a stationary distribution, okay? The stationary distribution, which we will call pi, the stationary distribution pi is basically the distribution where everything is at equilibrium. Okay, meaning applying the transition matrix to P, to pi, applying the transition matrix to pi does not produces a distribution equal to pi. So produces pi, meaning pi times our transition matrix P is equal to pi. Okay, so again, pi is a row vector or a row matrix representing the distribution across the states. Okay, so for our case, the stationary distribution, and we can talk about how we would find this, but the stationary distribution is where 4/7 of our values are at A and 3/7 of our values are at B. Okay, our transition matrix P again is 0.7, 0.3, 0.4, and 0.6. And we can see that if we multiply this together, we will end up getting the same thing here, okay? So if I do 0.4/7 times 0.7, I would have 4 times 0.7 over 7 plus 3/7 times 0.4. So 3/7 times 0.4, okay? So this is our first value, and then our second value is 4/7 times 0.3 plus 3/7 times 0.6. Okay, and so if I do this, I get 2.8 over 7 plus 1.2 over 7 for a total of 4/7. And over here, I would get 1.2 over 7 plus 1.8 over 7 for a total of 3/7. Okay, and so we can see that starting off with this distribution, 4/7 and 3/7, after applying the transition matrix P to it, I still get 4/7 and 3/7. Okay, and what this looks like is here I've got A and here I got B. Is that basically 12% or 4, yeah, I don't know what percentage, okay? Basically, the amount that's going from here to there, these amounts are equal. Okay, so, you know, oops, that's not what I wanted to do. Okay, basically, this triangle, or this arrow, okay, so the amount going from A to B, it equals those going from B to A. The number going A to B equals the number going from B to A, right? And so we're at kind of this state of equilibrium, and so the distribution no longer changes. We'd say the distribution is now stationary. Applying the transition matrix no longer affects the distribution that we have. Okay, all right, and so there's a theorem, and I'm not going to try to prove it, is that if you have a Markov chain that is ergodic and aperiodic, then no matter what your initial distribution, if you keep applying this transition matrix, it will converge to the stationary distribution. Okay, so if you have a Markov chain that is ergodic and aperiodic, okay, then no matter what your starting distribution was, if you repeatedly apply the transition matrix, okay, your distribution will converge to the stationary distribution. Okay, so this means, you know, whatever your initial distribution is, so you've got an initial distribution across the states, and if you multiply it by P over and over and over again, so as n goes to infinity, so applying P to your initial distribution over and over and over again, this will eventually lead to the stationary distribution. Close this out. Okay, let me kind of demonstrate this in R, just to kind of show this, and then we'll look on Friday at a way to kind of get our stationary distribution to be what we want it to be. Okay, so here's my initial state. My state, oh here, let's let's start off with the example that we had, okay? So my state has everybody in A and nobody in B, okay? And my transition matrix is what we've drawn. 0.7, from A to A is 0.7, from A to B is 0.3, from B to A is 0.4, and from B to B is 0.6. Okay. And so if I take my state and I multiply it times the transition matrix P, so I'm doing state times P, okay? I'm going to update my state, so I'm going to take the output of that and call it state, and then putting parentheses around it will print that out, okay? So I multiply state times P, and I ask, all right, please print that out. So exactly what we expected. If I start off with 100% at A, then after going through the transition, 70% will end up back at A and 30% will end up at B. Okay, and if this is my current state, which it is, okay, if my current state is 0.7, 0.3, and I apply the transition probability matrix again, we get 0.61 and 0.39, which is what our calculations showed, okay? Again, 70% of this will stay there, and so that's 49% plus the 40% of those at 0.3 will come back, and we get 0.61, so on and so forth. Okay, and if I apply the transition matrix again, starting with this state 0.61 and 0.39, then I end up getting 0.583, 0.417. Okay, and let's keep applying, and we'll end up with this 0.5749, 0.4251. Okay, and now I'm at 0.57246 and 0.42753, and we can keep applying, and we see that the amount that it changes a little bit less and a little bit less each time, and until I keep multiplying, and we see that at this point it seems like things don't change much, right? It goes from 0.57142865714286, 57142865714286, 57142865714286, and once I reach this state, applying the transition matrix P doesn't affect anything, okay? And we can compare this to what I said was the stationary distribution of 4/7, 3/7, okay? And 4/7, 3/7 is exactly that, okay? Is that all right? Okay. If I started off, so that was where I started with 100% at A and 0% at B. Okay. If I start off the other way with 0% at A and 100% at B, we can also see the results of this. Okay. So now I've got I still have the same transition matrix P. Okay, so if 100% started off at B and not A, okay, then after applying the transition matrix 1, I have 40% at A and 60% at B. Then I apply the transition matrix again, and I have 52% at A, 48% at B, and then I keep applying and applying the transition matrix over and over and over again. We can see that indeed we have reached a state where it no longer changes, okay? 0.5714286 and 0.4285714. So this state again is equivalent to 4/7 and 3/7. Okay, so this is just a very, very simple two-state Markov chain where some go from A to B and B to A. I'll link a little thing. There's a nice little picture here, explain visually, and here's a two-state Markov chain, and it kind of shows the probability of things transitioning from one to another, And then, well, anyway, okay. We'll look at this some more on Friday here. Okay. All right. We'll see you guys then.